Okay. Well, happy Friday. Yay. All right. I guess we'll get started then. Thank you to the 7 of you who came, which I guess that means, the other 68 of you who are watching online. Thank you for tuning in. Next Friday, we'll have our guest, Alex Krebs. I hope our attendance is much better than this. Maybe I'll make attendance required somehow. I'll have like a sign-in sheet. I don't know. We'll figure something out. Okay. Anyway, today I want to introduce the EM algorithm, and as far as this class goes, we'll just stick to a very simple version of the EM algorithm, and that is we're going to look at the EM algorithm for Gaussian mixtures. The EM algorithm can be kind of generalized and expanded to kind of any sort of situation where you have both missing values and unknown parameters. But let's introduce the basic ideas. And this video here from Ritvik Math is a very good video, and I like the example he used. So I'm stealing his example here. But basically, we use it in a situation where we have both missing data and unknown parameters. And so let's say we're told we have the values 1, 2, and x. So x is a missing value, and we say it's drawn. These values are drawn from a normal distribution, a normal where the mean is 1 and the standard deviation is 1. And then we say, well, what is your best guess for the missing value x? Okay. Well, if these values are just drawn independently from this normal distribution, then the most probable, the value with the highest probability for what x is going to be is just going to be the mean. So our guess for x will be 1. Okay. So that's simple enough. Okay. In this situation, the values are known, but the parameter is unknown. Okay, so let's say we're given the values 1, 2, 0, and you are told that they're drawn from some distribution where the mean is some unknown value mu. Okay, and standard deviation 1. And in this case, what is your best guess for mu? Well, our best guess for mu is going to be the maximum likelihood estimate. And for the normal distribution, if you have this distribution, the maximum likelihood estimate is just going to be the mean of your sample, the sample mean. So you do 0, 1, 2 divided by 3, you get a sample mean of 1. That's going to be your best guess for what mu is. Okay. And we now move to this scenario where we face both missing values and an unknown mean. Okay, so we're going to say we have some known values, 1, 2, but x is unknown, and these are drawn from some distribution where the parameter is unknown. And so now, what is your best guess for the missing value x along with the unknown parameter mu? Okay, and this is where we use the EM algorithm. And the EM algorithm is basically this iterative process, okay? An E step and an M step, okay? E for expectation and M for maximization. And here we can kind of take this iterative approach. First, we just start off with some arbitrary guess for mu, okay? And so let's say our initial guess for mu is going to be 0, okay? And if we take 0 as the best guess for the unknown parameter mu, then what's our best guess for x? In that situation, our best guess for x, the value we would expect to get for x, is going to be 0. And so now our data is 1, 2, 0. And then we say, okay, well, if our data is now 1, 2, 0, what's our best guess for the unknown mean mu? Okay. So looking at 1, 2, 0, we'd say, okay, we're going to use the mean of our sample and we would guess our unknown value mu to be 1. Okay, now that we have the unknown mu to be 1, we say, okay, what's our best guess for this missing value x? Okay, our best guess for the missing value x is going to be 1 now. Okay, and so now our data is 1, 2, 1, and we say, okay, what's the best guess for mu? So, using the maximum likelihood estimate for mu, we're going to get 1.333. Okay, and if I plug that back in, if I say, okay, well, using that, what's our best guess for x? We get a new thing, and then we kind of iterate back and forth, back and forth, back and forth. Eventually, we'll converge to where x is 1.5 and mu is 1.5. Right? And that's kind of an overview of what the EM algorithm is going to be doing. Okay, we kind of go through this iterative process to get both the missing values and the unknown parameters. And we're going to apply this to Gaussian mixtures, okay? And I don't know, if you were to take another course or something and you cover the EM algorithm, you might cover kind of a more generalized form. And the more generalized form is a little bit tougher because you have to kind of generalize this idea of, how do you get the expected values, right? And it's not necessarily, the values for them. What are your expected values for x, the unknown values, missing values? And then how do you get your maximum likelihood estimate? And depending on the distribution, depending on the setup of the problem, these could actually be rather complicated. It can get quite messy. And so the generalized math form can be a little bit intimidating looking. We'll stick to kind of this simpler example, and I hope it'll be okay. So when we do the EM algorithm for Gaussian mixtures, what we're going to have is we're going to have data. And the data consists of points that have been generated from basically a mixture of Gaussian distributions, right? So one way you could kind of think of this is, okay, so we say height. Often we treat height as this Gaussian distribution, this normal distribution. And for the simplicity of this example, let's just we'll say the height of the population can be considered as a mixture of Gaussians for male and Gaussian distribution for female height. Okay, and again, simplified scenario where we're just looking at the distributions of two genders, and certainly we could probably come up with something that is more inclusive. And what we can say is that heights themselves could be treated as kind of a mixture of normal distributions, right? In our case, we'll look at a two-dimensional Gaussian. So we're going to look at the multivariate normal distribution, and we'll say our data consists of a mixture of multivariate of several of these Gaussian distributions. But the missing data, okay, is which distribution a point belongs to, okay? So when we observe some person's height, a person is 5'6", okay? We don't know which distribution this value came from, okay? So we don't know which distribution it comes from. That's the missing values, okay? We also don't know the mean and variance of the normal distributions, okay? We don't know the mean and variance of distribution 1. We don't know the mean and variance of distribution 2, or things like that. And so we're going to use the EM algorithm to kind of iteratively figure out both the unknown parameters and the unknown cluster assignments, okay? So this is an unsupervised learning technique, in that we're kind of like forming clusters, but we don't, and we're saying the data come from mixtures of Gaussians, but we don't know which distribution they're coming from. We don't know the means and the variances, and so it feels like this. At first, it can feel a little overwhelming, okay? But we'll go through it, okay? So here I'm gonna let you in and on In our case, we are going to generate our data ourselves, and we can and because we are generating the data, we can know the answers. In that, here I'm going to say we have 3 distributions, 3 multivariate normal distributions. We have distribution 1 or component 1, component 2, component 3, and we're going to say component 1 makes up 50% of our data. Component 2 makes up 30% of our data, and component 3 makes up 20% of our data. So we have this alpha vector that tells us the relative proportion that comes from each distribution. And then we're going to say, okay, component 1 is a 2-dimensional multivariate Gaussian, 2-dimensional Gaussian, where the mean is 0, 0, and this is the variance. The variance is this sigma matrix 9009, in that basically it's a big circle, right? So it's x and y are independent and things like that. Okay, component 2 has a mean of 4, 4. Its variance is a lot smaller, 1, 1, but there's high covariance, 0.9, 0.9, high covariance here. And then component 3 has a mean of -4, -4, and its variance is 2, -1, -1, 2, so there's some negative covariance there, okay? And when I generate, let me just generate the data here. This is what the data will end up looking like. We've got the big blob. This is component 1. 50% of the data come from the big blob here. 30% come from this component where the mean is 4, 4, and there's high covariance here. And then we also have kind of this thing. This one's a little bit harder to see, but there's another component at -4, -4, and there's some negative covariance here. Okay, do we see this? Okay. Oh, here it is. Okay, so when we label them with their points, we can see the black dots come from the first component with a mean of 0, 0 and a variance of 9009. Okay, and then this one is a mean of 4, 4, and there's high covariance, and then we have a mean of -4, -4, and there's some negative covariance. So these are the 3 components that are being mixed together. Okay, and when we specify the mixture model itself, okay, we use this kind of this formula, in that we have k different components. Okay, so in our case we have three components, and basically we have to take the mixture weight representing the probability that a certain point came from a certain cluster, and then we're going to multiply it by the PDF that's associated with that cluster. Okay, so we're going to say, hey, what is the probability, okay, of some point x, and our x is a point in 2-dimensional space, given the parameters theta, okay, and the parameter theta consists of basically all of the parameters that we need. So there's alpha, the 3 mu's, and the 3 sigmas, okay? So theta just gathers all of those things, and this is going to be the mixture weights, which is 0.5, 0.3, 0.2. That's unknown to us though, okay? But you know, the key is that the sum of those mixture weights add to 1. And then we have the PDF. In this case, it's the multivariate normal PDF. So you do have to make some assumptions about your data. You have to assume what distribution it's coming from. In our case, we're going to say we've got the multivariate Gaussian PDF. And so this is the PDF of our data given, and Z is basically a vector of indicator variables, and it's either it belongs to cluster 1 or cluster 2 or cluster 3, and basically Z is 1s and 0s, okay? So in our case, we have basically, yeah, the membership weight, or the membership class of a point X. Okay, so to kind of generate the data, this is what my generated data look like. I've got my vector alpha. I've got the coordinates of mean 1 is 0, 0, mean 2 is 4, 4, mean 3 is -4, -4. And then the sigma matrices are, 9009, 1.9.91, and 2 minus 1 minus 1, 2. I gather the means together into a list. I gather the sigmas into a list there. And then to generate the data, I'm going to use multivariate normal. I'm going to say I want 1,000 points. And I'm going to just say, first, sample a value 1 through 3, okay, using the probability vector alpha, okay? So generate 1 with probability 0.5, generate 2 with probability 0.3, and generate the value 3 with probability 0.2. And whatever that is, whatever value k is, look up that value for the means in the list of means, look up the sigma matrix in the list of sigmas, and then generate one random value using the random multivariate normal. Okay? And also store which component belongs to. And so when we do that, this is the data. It comes in not labeled. So we look at this, and the problem that we're specifying is identify 3 clusters. We're going to say look for 3 clusters and figure out what the mean and the variance is for each of these clusters. Okay? And you don't know the assignments of any of these points. So can you identify 3 clusters along with their means and variances without knowing actually which thing, right? It feels like a big problem, okay? Here we have the answers, but again, we don't actually, in real life, when we look at the data, we don't know what the answers are. We generated the data, so we have the answers. But in real life, it comes in like this, and we're supposed to try to recover these, the parameters, along with the value assignments, okay? And so, the problem, one of the hard parts of this problem is that, what if you have a point right here? So there's a point at the end of this arrow here, and we say, hey, which cluster do we assign this to? Is it part of this cluster right here that is centered at 4, 4 with high covariance? Or is it part of the larger cluster centered at 0, 0, which has high variance? Which point does this assign to? Okay, I think we can say, well, surely it's not going to be the cluster down here. Okay, and so that's part of the tricky part is when you look at this, we go, well, how do we assign things to clusters? Oh, okay. Before I forget, first view quiz answer is E. E as in elephant. E as in elephant is your first view quiz answer for today. E. Okay, so what we're going to do is we are going to use a probabilistic assignment, okay? So in k-means clustering, we said this point is closer to this centroid, therefore it belongs to this cluster. This point's closer to that centroid, it belongs to that cluster. And it was kind of this strict, you're in this cluster or you're in that cluster. Here, we're going to use a probabilistic assignment. So rather than strictly assigning one point to a cluster, we're going to use the Bayes classifier, okay? We're going to use the Bayes classifier to get a probabilistic assignment. So we use the Bayes classifier, which we covered earlier in our course, and we're going to say, okay, it belongs to this cluster with probability 0.8. It belongs to this cluster with probability 0.19. It belongs to this cluster with probability 0.01. Okay, we're going to have a probabilistic assignment for the different clusters. Okay, and then now once we have these membership weights, okay, and we say, okay, these points are kind of belong to cluster 1. Using that, let's calculate what our mean and variance is, okay? So once we have the membership weights, we calculate the parameters of each cluster. So we're going to get, we calculate the mean by using weighted mean. We calculate kind of this variance covariance matrix by using a weighted version of it, okay? And basically we do that, and then we maximize, and so that's the M step. This maximizes the likelihood of the values assigned to the cluster. And then we go back and we calculate all right, now that we have a new mean and new variance for each of these clusters, let's figure out what cluster each point belongs to. And again, that's going to be the membership weight. So that's going to be kind of trying to figure out our missing values of which cluster these things belong to. That's the E step. And we go back and forth, okay? And so you can kind of think of the EM algorithm as a blend between k-means clustering and the Bayes classifier. So in k-means clustering, we said assign the points to this cluster, recalculate the centroid. Assign the points to the cluster, recalculate the centroid. Assign the points to the cluster, recalculate the centroid. Basically, we're doing something very similar, except when we assign the points to a cluster, we do it probabilistically. So we say there's a 70% probability it belongs to this cluster. There's a 60% probability it belongs to this cluster. There's a 90% probability it belongs to this cluster. And then once we have these probabilistic assignments, then we say, okay, well, what's the centroid or what's the mean of this cluster? And we do a weighted version of it, taking into the probabilities. So things that have a high probability, we kind of use almost their full weights. And things that have a very low probability of belonging to the cluster, we weight those less. Okay? So when we calculate the membership weights, this is our E step. This is kind of like figuring out the missing value of which cluster a point belongs to. We use the Bayes classifier. Okay? We're going to say given the x values of the point and all of the parameter values, the weight and probability that a point belongs to cluster K is we're going to find the likelihood times the prior divided by the marginal. We're going to say what's the probability, the likelihood that this coordinate, okay, let's say we have the coordinate 3, 3, okay? What's the probability that a coordinate 3, 3 is generated from this distribution, okay? We multiply it by the prior probability of belonging to that distribution, okay? And then we do that for all of the different possible clusters, and then we divide that, okay? So we use the Bayes classifier in this step. So how do we get how do we get this? Okay. So the membership weights, this prior part, the alpha sub k, okay, is kind of the prior probability, at least based on the previous iteration, that a point belongs to some cluster k. And so in this traditionally, we would just say, okay, how many points belong to cluster K? So if we have 1,000 points and 500 belong to cluster 1, we'd say there's a 50% probability of it belonging to cluster 1. And if 270 belong to cluster 2, we'd say there's a 27% probability that belongs to cluster 2. Okay? However, this sum here, the number of points that are assigned to the cluster is not really an integer. Okay? It's not, because the points don't actually get assigned to clusters, right? They only get membership weights. So we just kind of sum up the weights. We sum up all of the weights, and we're going to just say, okay, this point has a 99% probability belonging to a cluster 1. This point has an 80% probability belonging to cluster 1. And so when you add those two, you get 1.79. So you have 1.79 points belonging to cluster 1. Or something like that. So you're just going to add up the weights. So you're not going to get an integer here, but you can kind of think of it as the number of points that are assigned. It's just like the total sum of the weights of things that belong to the cluster. Okay, so that's going to be our membership weights. So that's going to be this prior value. Okay. How do we get this likelihood? Okay. The likelihood is just the multivariate normal density. Okay. So we just say, okay, well, here is a point X, okay? And we just use the multivariate normal PDF, okay? So we just use the PDF of the multivariate normal distribution. We can just use DMV norm. We take in the value, and we use kind of our current estimate of the mean vector and our current estimate of the sigma matrix to get what is the likelihood that a point that a distribution would generate this particular point. Okay, and we calculate this again across all three clusters. Okay. The M step, we're going to calculate. So once we have the assignments, now, so that's the E step. We have to figure out the membership weights. Okay, so we do that, and then the marginal, you just sum across all of the numerators, and you get your weights. Okay, so now once you have those weights assigned, we go through and we say, okay, where's our new, basically our centroid, except in the EM algorithm, it's the mean and the variance. Okay, so we need to recalculate the centroid and the variance. And so once you've calculated the membership weights, we're going to kind of recalculate the centroid of each of these clusters. And here we're going to do this by using a weighted mean. Okay, so we just take all of the points, we multiply each point by its weight that it belongs to a certain cluster, we add them up and divide by n. Okay, this formula is very much like the way we calculate the centroid for k-means clustering. Okay, at k-means clustering though, instead of a w you had a z, and the z was a 0 or a 1, right? And when you divide by, you didn't divide by n, you divided by the sum of z, which was basically n. Okay, how many points belong to that cluster? So instead of a z, which is a 0 or 1, we have a w, which is now some decimal value between 0 and 1. Okay, we have a decimal value between 0 and 1. And so, so we take each weight, we multiply it by x, and then we divide by nk, which is the sum of the weights. Okay, so that is points that are highly likely to be in cluster k will have a membership weight close to 1 and will contribute more to the value of the mean, whereas points that are unlikely to be in cluster k will have a membership weight close to 0, and they're not going to influence the value of the mean very much. And then we estimate the sigma matrix, okay? And so the sigma matrix is basically the formula, if we just hide this part, this is just the formula for getting your sample variance, okay? Except sample variance you divide by n minus 1, okay? But basically it's the same thing except we're doing it weighted, right? So we take x minus the mean, mu k, so we calculated the mu k in the previous step here. Okay, so once we have the cluster's centroid, we do each point minus the mean times x minus the mean transpose. That's going to give us a 2 by 2 matrix. And then we weight that by w. Okay, we multiply it by the membership weight. And then we sum all of those up and divide by nk, which is the sum of the weights. And this will give us basically our weighted estimate of the sigma matrix. Does that kind of make sense, what we're doing? Right? So I want to kind of make sure that getting the centroid and getting the variance, or the mean and the variance for our clusters make sense. I also want to make sure that how we calculate our membership weights also makes sense. Because those are kind of the two biggest components of this thing. You have to calculate the membership weights using the Bayes classifier. And once you calculate the membership weights, you have to recalculate the mean and the variance using basically maximum likelihood estimates. Okay, this would be the maximum likelihood estimate of this thing. In our case, with the Gaussian mixture, like I'm giving you the answer of what the maximum likelihood estimate is. Perhaps a harder problem is like I don't give you this answer and I just say, hey, figure out what the maximum likelihood estimate would be in this scenario where you have weighted membership class categories, right? And that's a little bit tougher. Here I'm kind of giving you the answer, but you figure out your maximum likelihood estimate for the mean and the variance, and once you have that, you figure out what your membership weights are. This is using the Bayes classifier. So, okay, so let's take a look. Let me go ahead and give you your second view quiz answer. Second view quiz answer today is C. C as in cat. C as in cat. C as in cat. Okay, so here's our data. It's not labeled at all. This is how we see it. Okay, these are the true assignments. The true assignments. Okay, and so down here, we have a mix of points that belong to this cluster, as well as points that belong to the center cluster, but they just ended up out in this territory. Okay, same as out here. We have points that belong to the red cluster and points that actually belong to the central cluster but get thrown out here. Okay. I've hidden the rest of my code here because your homework is to do this. Write the code to do this. Okay. All right, and so here we're going to just start off with initial random arbitrary guesses for what the parameters are. Okay, so I'm going to say we've got one. We're going to start off with one mean at 0, 0, one mean at -9, -9, one mean at 9, 9, and all three of them are going to have 1, 0, 0, 1. Identity matrices as the kind of covariance. So these circles represent kind of the contours of the multivariate normal centered at 9, 9 with mean 1 and variance, diagonal matrix 1, 0, 0, 1, and so on and so forth. And if you do this using the Bayes classifier, it says these points are most likely to belong to this cluster. These points are most likely, the black ones are most likely to belong to the center cluster, and these red points are most likely to belong to this cluster down here. Okay. Now, there is something misleading about these colors here. Okay, so when I color them, I can either only color them as red or black or green. Okay? But the truth is that along this border, when we use the Bayes classifier, this one is like 51% red and 49% black, and this point over here is like 51% black and 49% red. Okay? It's just really, it's too hard to try to color them that way, and our eyes aren't actually really good at kind of like, you could color the states rather than red or blue. You could color them purple and stuff, but it gets really hard to tell the difference between these things. So I've decided to just color them red or black or green based on whichever class got the most probable assignment. Okay, but it's not really that they're assigned to red and these are assigned to black. Okay, it's right along the border, it's 51% red, 49% black, therefore it gets colored red. Right along the border on this side, it's 51% black, 49% red, and therefore it gets colored black, okay? These ones probably are like 99.9% black, and these ones over here are probably 99.9% green, okay? But they all just get colored green the same, right? Is that okay as far as what's happening with the colors? So they're not actually assigned to red, black, or green. They're just getting kind of colored that way, but the membership weights are probabilistic. Okay, so we will iterate, and so based on what got assigned to green, what got assigned to black, and what got assigned to red, we're going to say, okay, calculate what is the centroid, the weighted centroid of green. Okay, along with the variance that best explains green. Okay, calculate the weighted centroid of black along with the variance that best explains the points in black, and calculate the weighted centroid of red along with the variance that best explains the red. Okay, and so at the next iteration, this is what we get. Okay, and so already we can see by having to account for the variance in our data, the variance for this cluster colored in black gets very big. Okay, and then we have these points in green, and it says, okay, here's kind of our estimated thing. And so so after one iteration, these are kind of our new ellipses drawn to show what the multivariate normal distribution looks like in that case. And then I think I've also kind of done both steps of recalculating along with the reassignments in this thing, okay? So back here, all of these points were green, and so you can see already with the reassignments, these points got colored as black because they're kind of far away from this this kind of ellipse here, okay? And again, we can only color the points one color at a time, even though they're truly probabilistic. Okay, and so I will kind of iterate through and just show you what happens as the EM algorithm continues to run. So at the next iteration we get this, next iteration we get this, and then we get this, and this, and we keep running, and this is what it converges to, okay? I mean, you could keep running it and it probably just gets tweaked a little bit more and more, but let me just reverse. I just think the animation, the animation looks cool. Okay, whoops. All right. And so again, one thing is that these all get probabilistically assigned to green. Highest probability is green. These ones are all probabilistically assigned to red. Highest probability is red. Again, in reality, okay, so and then after letting it run for a while, it converges to this, okay? And so these all get probabilistically assigned to red, these get probabilistically assigned to green, these all get probabilistically assigned to black, okay? Whereas in reality, there is a mixture down here, okay? But as far as the final EM clusters, these highest probability over here is going to be this cluster, okay? We see the label switching problem, okay? Again, what we call the red cluster, green cluster, and black cluster is just arbitrary. And so in this case, the original data, this was the red cluster, and this was the green cluster, and this was the black cluster. Here, it kind of switched out, right? So I think I saw a question like this on CampusWire, but during your confusion matrix, you're not going to get necessarily down the diagonal. But what you do want to see is within one row, for the true values, you want to see almost all of them form in one column. Okay, so it might not be in the diagonal position, but if it says for the first thing, if it says 99 belong to this one and only one belongs to something else, that's pretty good. Okay, so that's our final clusters. Okay. What if we had different starting locations? Okay, so here, what if I started off with a mean up at 0, 10, a mean at 0, 0, and a mean at 0, negative 10? Will it be able to recover the true assignments? Okay, and so kind of right away, by taking kind of the weighted means, at the next iteration, this gets drawn over to there. Okay. Over here, where is the mean of all of these points? It gets drawn over a little bit over there. The mean of this is that, and this, and again, we let it run, and it kind of it ends up finding it correctly. So that's encouraging. Okay, so that's what we get at the end. I guess that was it as far as the slides I had prepared. But it is subject to, you could start off with some really bad assignments, and some really bad initial assignments could end up converging to the wrong location. So in our cases, with my two different starting locations, they ended up kind of converging to the correct spots. Similarly over here, it ends up converging to the correct spots, and that's that. Okay. So the EM algorithm, I think it's pretty cool in that, there's a lot of pieces that are missing, but we kind of go through this iterative process of let's try to do our best guess for what these unknown parameters are. And now that we have these unknown parameters, let's do our best guess for figuring out our missing values, okay? And in our case, in this Gaussian mixture case, we use the Bayes classifier to figure out our missing values. We use kind of these weighted means and weighted variance matrices to figure out our best parameters. The generalized EM algorithm, again, is a bit more complicated just because it kind of takes in, you have to kind of consider all of these different possible scenarios, and you say, well, how do we maximize, what is the maximum likelihood estimate for the parameter estimates, okay? And that for the Gaussian ones, it's pretty straightforward, but for other distributions and examples, it can be hard. And then, how do we figure out what our missing values are? And again, depending on the scenario, it can be kind of trickier or difficult to figure that out. Okay, let me go ahead and give you your last view quiz answer for today, which is the letter B. B as in bear. B as in bear is the last view quiz answer for today. Okay, we'll end there. Have a great weekend, and we will see you on Monday. So see you then.